Hi everyone, and welcome back to the College Physics series. In today's lesson, we're going to be talking about the strategies that we use to solve kinematic problems involving constant acceleration. But before we get started, be sure to download the guided notes in the description so that way you're able to follow along with me throughout this lesson. So, thank you for being here, and let's get started. So let's get started on today's lesson on solving one-dimensional motion problems. Today, we're going to focus on 5 key steps. The first step we're going to follow is draw a picture. The second step we're going to follow is to identify the knowns and unknowns. The third step we're going to follow is to choose the right equation. The fourth step we're going to follow is to solve for the unknown or unknowns. And the last step we're going to follow is to check our units and answer. So this list of 5 steps, this is just an overview. We're going to get into more detail later in today's lesson. Before we continue on into this lesson, let's quickly review the basics that you need to know prior to watching this video. The first thing that you need to know is that one dimension of motion refers to movement along a straight line. One dimension means just straight left or right, left and right, that's one dimension, or straight up and down. That is another dimension. The next thing that we need to know coming into this video are the big 3 kinematic equations. These are the big 3 kinematic equations, and if you're unfamiliar with these, check out my previous video where I explain these equations in depth. So let's go ahead and talk about our problem solving approach. In step 1, we need to draw a picture. Drawing a picture helps us to visualize the situation, organize our information, clarify the direction of motion, and to simplify complex sounding problems. Also, what happens in step 1 is where we categorize the type of motion. And what I mean by that is that we need to ask ourselves, is this an example of uniform motion, or is this an example of constant acceleration? And so when we categorize the type of motion, then that leads us down sort of a flow chart of what equations are applicable. Step 2, identify knowns and unknowns. This is important because this is where we write down what we know and what we are looking for. Identifying the knowns and unknowns is an important step because it helps to organize the information that we've read and establish a clear goal of what we are trying to solve for. Step 3, choose the right equation. Choosing the right equation is important because physics is not just math. You cannot just grab any formula that looks like it would fit the situation and then plug in numbers and expect an output. The importance of choosing the right equation is that the equation must model the type of motion. It must model the physical scenario appropriately. Only then is it a good equation to choose. So the knowns and unknowns should reveal the appropriate equation to use. And we covered that in the previous video by playing the little game, placing the check marks on top of the knowns and the question marks over the unknowns. And the equations that we were able to use were the equations with only one unknown variable. Step 4, solve for the unknown. When solving for the unknown, remember we're going to symbolically rearrange the equation for the unknown variable. Lastly, step 5, check your units and answer. So in step 5, when we are checking our units and our answer, we must make sure that our answer, after the math is all simplified out, the dimension or the unit of measurement must be correct. If your final answer is for the time interval and your answer is 15 meters, you've done something incorrectly. So what we expect when the question is asking for some sort of time interval is an answer in seconds. If you do not get something that outputs seconds, then you've made a mistake and you must recheck your work. The next part of step 5 is to ensure that the answers we get make physical sense. If we are calculating the speed of a baseball from a baseball pitcher and we get 1,000 miles per hour using realistic data, then we can pretty safely assume that we've made an error somewhere along the way. Similarly, if we're using realistic data for a snail and wanting to create a position time graph and we get that it's moving at a constant velocity of 1,000 miles an hour again, this is pretty way off, not realistic for a snail. So that's how we can ensure that when we are done with our problem, that we are on the right track. Okay, so that summarizes our problem solving approach. Now, let's go ahead and see a few examples and see this in practice. So we have example 1. Example 1 reads, a car accelerates from rest at 3 meters per second squared for 5 seconds. How fast does it go after 5 seconds and how far has it traveled? Draw a picture and obtain the known and unknown quantity. So we have a car car starting from rest. So I'm going to draw my car right here. And this starting point is where I'm going to find my initial position. This is where I'm going to find my initial velocity, and I'm going to write it in a sort of different way than what we've seen. This is velocity. X means it's horizontal because this is moving left and right. If it were moving vertically up and down, then I would put a Y, and I'm going to put in parentheses. So horizontal velocity, initial. And then this is where I'm going to find my initial time. So if I want to find information about any one of these variables, then I'm going to look at this spot. Later on, the car has accelerated. And at this position, this is where I'm going to find information about the car's final position, its final velocity, or I should say final horizontal velocity, and the final time. Drawing a motion diagram for this car, the next step is just to label the knowns and unknowns, and we are done. So here's how I like to label my knowns and unknowns. What I'm going to do now is that I'm going to reread the paragraph and obtain my known quantities and what the question is asking me for. It reads, a car accelerates from rest. Remember that rest word means that my initial horizontal velocity is 0 meters per second at 3 meters per second squared. So it accelerates from rest at that rate. So my acceleration, I'm going to write horizontal acceleration. I guess I should put an X there as well if I'm putting the X for the velocities. That is 3 meters per second squared. And it does that for 5 seconds. 5 seconds is the total time. That gives me my time interval, 5 seconds. How fast does it go after 5 seconds? So I'm looking for some final velocity, and then lastly, and how far has it traveled? So I'd be looking for the displacement, which in this case would be equivalent to the final position, because the initial position, I would call it 0. So I would say that those two are equal. And of course, the same would go for the delta t. The delta t would be equal to the final time, which is 5 seconds, because the initial time would also be 0. And that completes example number 1. All we had to do was draw a picture and then obtain the known and unknown quantities. Let's do another example. So here's example number 2, and it reads, a rocket accelerates upward at 20 meters per second squared for 10 seconds. What is its final velocity and how high does it go? So my first step, I need to draw a picture to model this situation. Since I have a rocket going upwards, that's another type of one-dimensional motion, up, down. And the previous example that we did was just left and right. So I need to model this vertically. Now my rocket's going to start from there, and at this position here, this is where I'm going to find my initial vertical position, my vertical velocity initially, and my initial time. And then 10 seconds later, let's say it's up here. And at this position, this is where I'm going to find my final vertical position, my final vertical velocity, and my final time. Because this object is accelerating in a motion diagram, that would be my initial spot from the ground, and then it would get smaller, and then it would get quite large pretty quickly, and so on. So I know that my acceleration is pointed upwards. And of course my velocity vectors, which I can draw in green, point upwards as well between each of these frames. Because remember, one thing about acceleration and velocity is that an object speeds up if the velocity vectors point in the same direction as the acceleration. Let's identify the knowns and unknowns. So it says a rocket accelerates upward at 20 meters per second. So I know my AY is going to be 20 meters per second squared. And I'm writing AY because that's my vertical acceleration. It does that for 10 seconds. My delta T is 10 seconds. And again, delta T is going to be equal to TF because my TI starts from the beginning, that's 0 seconds. And of course, the same thing will happen for my YI. This is 0 meters. The question is, what is its final velocity? So I'm looking for my final velocity, and I am looking for how high it goes. I'm looking for this final position, which of course in this case will be equal to the vertical displacement because it is just moving along a straight line. I'm missing something because I got this down, I got this down. I'm looking for this. I'm missing my initial vertical velocity. If you notice, the example doesn't mention anything about it, but here's what I have to do. I need to use a little bit of logic in this scenario. And so I need to say, if I'm about to watch a rocket launch into the air, how fast is a typical rocket moving before it launches? Well, a rocket will just be sitting there before it blasts upwards. So that means I can reasonably conclude that the initial vertical velocity is 0 for any rocket that has not taken off yet. So at the beginning of any rocket's motion before it flies upward in the sky, it is not moving on the ground. That's why I can safely assume that my initial vertical velocity is 0 meters per second. If you remember, we have 3 tools to help us solve for this. So these are the big 3 kinematic equations for constant acceleration motion, but they look a little different. If you notice, wherever there used to be an X, there is now a Y because this scenario is vertical. And also before, I did include these Y's or X's in there. I just wrote VF equals to VI plus A times delta T. That's what I used to write before. And that's a very general equation. But what I've done to this equation is that I've added subscripts to further clarify information about my problem. If I say If I use this, then it gives me no information about which direction the object's moving. But if I use this one, it clearly identifies that in my work, I was solving a problem in which the velocity was vertical, the acceleration was vertical. Whereas this first initial one does not display or not give any information like that. The way that it's written here is a little bit more useful. It contains a bit more information, and more information is always better in science. Let's figure out how we can solve for VYF and the final vertical position. Let's play the game. Anything that is a part of our knowns, we're going to label it with a check mark. So accelerations, check. There they are. My delta t all gets checks. My initial velocity, that gets a check, and that's 0. And my final velocities, they get question marks. Like I said, I know this ti and this yi, so yi right here gets a check as well. And I'm looking for delta y, and I'm looking, which is the same thing as this y-app. So if you can tell here, in the third equation, I have 2 question marks. Therefore, I cannot use that formula. What I can do is I can use the first one to solve for the final velocity, and then I could use the second one right here to solve for the final position. So let's do that. So if I remember correctly, my initial velocity is 0. So therefore, I can plug in a 0 in there, and that's just going to cancel it out. Therefore, I can write this. So my final velocity becomes just the acceleration times the time interval. And I know both of those, so I can just plug them in. So I get 20 meters per second squared times 10 seconds. 20 times 10, that is 200. And then I get seconds to be multiplied by, it's seconds on 1 seconds on top, and then a second squared in the denominator. So that's going to cancel out to be meters per second, which is exactly how I measure velocity. And that solves for the final velocity. Next, let's use the second formula to solve for the final position. Okay, so let's look back again. My yi is 0 right here. And also my vyi again is 0. So therefore, these terms right here are going to cancel out. And I cancel out this delta t because it's being multiplied right here by the velocity. So it's velocity times the time. So 0 times anything is still 0. And this is how my equation is going to look like now. So I get 1/2 ay times delta t squared. Now I can plug in my numbers and get my answer. I'm first going to do the 10 seconds squared, and that's going to give me 100 square seconds. Square seconds is going to cancel out with the second squared. Finally, that final position will give me 1,000 meters. Actually, the last step, I need to assess. Does this make sense? That the final position is 1,000 meters high when this rocket accelerates at 20 meters per second squared for 10 seconds. That's pretty reasonable. I would need to question myself if my final position was maybe 50 meters or 100. That wouldn't make too much sense at all. And then my final velocity. I do expect that this rocket is moving quite quickly, and 200 meters per second is not a slow velocity at all. So that makes sense to me as well. And that will complete example number 2. We're going to do one last example, and we're going to step it up a notch. So example 3 reads, a car travels at a constant velocity for 15 meters per second for 10 seconds, and then accelerates at 22 meters per second squared for another 5 seconds. What is the total distance traveled? Now, things just got a little bit complicated because at first, for the first part of the motion, this object is moving at a constant velocity. Okay, so if my object's moving at a constant velocity, then the constant acceleration equations do not apply. So I have one section for 10 seconds, and then all of a sudden the object accelerates. So I have 2 separate motions. So when we are drawing this out, we need to be purposeful with how we are labeling things. So my car is going to start here. This is where it's going to start its position. This is where it's going to start its velocity, and this is where the initial time will be at. Now, I cannot label this. Well, I can, but it'll be very complicated to use I's for initials and F's for finals. Because we're going to have multiple points in this object's motion, I'm going to have to number them as 1, 2, and 3. So this is going to be x1, the first position, vx1, the first velocity, or in this case, the initial velocity, and then t1. So this is going to represent the very beginning. And then the car is going to reach some other spot over here. And this will be the point where the object will undergo the motion chain. So at this point, right at this point, this is x2, my second position, vx2, my second velocity, and then t2, my second time. So everything right here, my horizontal acceleration is 0 meters per second squared. There is no acceleration. That means constant or uniform motion, constant velocity. That's what this left side experiences. Then on the right-hand side, my car is going to accelerate. Here I have my acceleration section. It's going to be 22 meters per second squared. And over here is where I'm going to find my third position, my third velocity, and my third time. Remember the total distance traveled. So I need to find the distance between x1 and x2, and then I need to find the distance between x2 and x3. When I add them all up, or when I just compare x1 and x3, I'll be able to get the total distance traveled. So that is step 1 essentially. This is drawing a picture, but we need to be very purposeful and thoughtful when we are labeling our diagrams. Our next step is that we need to identify the knowns and unknowns. So I'm going to label x1 as being my starting point. Therefore, x1 is going to be equal to 0 meters. So I'm going to call this my 0. T1, since it's beginning, it also gets a time of 0 seconds. My vx1, I'm going to actually, we need to reread. This car is traveling at a constant velocity already at the beginning. So therefore, my vx1 is already 15 meters per second. I almost made the mistake of calling it 0 because I'm used to those other types of problems. But we need to always go back and reread. So it covers this constant velocity section for 10 seconds. So that means my T2 is 15 seconds later. So my T2 will be, 10 seconds. It's 15 meters per second, but T2 lasts all the way up to 10 seconds. Then we accelerate at 22 meters per second squared for another 5 seconds. So between T1 and T2, that was a total of 10 seconds. And then for the next 5 seconds, we are accelerating. So T3 is going to be 10 plus 5, which is going to be a total of 15 seconds. So Vx2, that's something else that we also know, because starting from x1 all the way to x2, we are at constant velocity. As soon as it passes x2, then it starts to accelerate. So Vx2 will also be 15 meters per second. Now what we're trying to find here was that we need to know what x2 is and we need to know what x3 is. Then Vx3, well, that is something that we don't know, but it's also something that we don't need to find out because it's not going to answer the question that's being asked of us. Okay, so I need to find the distance from x1 to x2. Since this is uniform motion, there's no acceleration, I can use this equation to do that. And I'm going to label this step 2. Here's my step 3. This equation is the equation of uniform motion. xf equals to xi plus the average velocity times the change in time. Notice how this is a very general way of writing it, but I have an initial position and a final position. But in this scenario, I have 3 positions, x1, x2, and x3. So that's why I need to be more specific when I'm labeling this out. But let me show it to you step by step, the evolution of how we get to become more specific with our symbols. So not only do I have different positions, but I also have different times. So let's rewrite it like this. Instead of delta t, I need to specify between which time interval am I seeking the final position. And in this case, I can only use this equation for when there is constant motion. So that's going to be between t1 and t2. Let's become more specific. The final position will be x2. The initial position will be x1 plus the initial velocity or the average velocity. That is, it's the same. Vx1 and Vx2 are the same. So I can just write Vx1 as the average velocity multiplied by t2 minus t1. If you notice, all of the f's got a 2, all the i's got a 1. That is how I'm being specific. So when someone's reading your work, they can notice that, okay, you're finding information only throughout this section right here. And I can check that this equation even applies because I know that there's no acceleration. So if someone else is reading your work and you've used a constant acceleration equation, I could have already tell that you've made a mistake. You've made a mistake with your assumption. Let's continue. So I'm looking for x2 and we're going to plug in our numbers now. I'm looking for x2. I know my x1 is 0 meters plus this initial velocity of 15 meters per second multiplied by t2, that is 10 seconds, minus 0 seconds. So the position at x2 is going to be simply 15 meters per second multiplied by 10 seconds. And that's going to give me 150 meters because seconds cancels with the seconds there. So the position at 2 is going to be 150 meters. And that's something that can go in my knowns. x2 equals 150 meters. Perfect. I'm halfway there. So now I know from x1 to x2, this car has traveled 150 meters. Now I need to find the distance between x2 and x3, but I can no longer use constant acceleration because, I can no longer use uniform motion because now I have constant acceleration. So let's go ahead and find that in our step 4. In step 4, we're going to use this equation of constant acceleration. So this is a very general equation. What do I mean by final? What do I mean by initial? And what time interval am I even looking at? What's the initial velocity? So let's specify this and let's expand the delta t's. My final position in this case is going to be x3. That's what I'm going to be looking for. I'm looking for x3. And where I'm going to be starting my motion is at x2. So my xi in this case will be x2 and then my xf will be x3. So the finals will get the 3's and then the initials will get the 2's. So let's rewrite our equation with this new change. By writing it like this, I can easily come back to my knowns and unknowns and read what t3 is, what t2 is, what x2 is, and what vx2 is. So I'm going to now substitute all of those numbers into this equation. So there we have all the numbers plugged in. Now we just need to simplify the math. Now let's simplify further. And again, we simplify further. And lastly, we get that the position at x3 is 500 meters. Therefore, we've answered the question, what is the total distance traveled? And that is 500 meters for this car. What I've shown you here is how to use the kinematic equations to solve a problem involving 2 types of motion. What I'm going to show you now is the shortcut method. We could actually use graphs to our advantage to find the answer to this problem in a much simpler way. Let me show you. So we could use graphing to answer this same question instead of using all of the kinematic equations. And the idea that we are exploiting is that the displacement is equal to the area under a velocity time graph. How do I know I can use a velocity time graph? Well, because it gave me the velocity at the very beginning of the motion. Constant velocity 15 meters per second for 10 seconds. And then it gives me the acceleration for the next amount of time. So if I can draw the velocity time graph, then all I need to compute is the area under the graph and I'll have my answer. So let's draw the graph together. So I'm going to label the x-axis as being the time, and I'm going to scale it by every 5 seconds. And then the vertical axis, I'm going to label it by 15s. So here's what I know. I know that for the first 10 seconds of this motion, the object is at a constant velocity 50 meters per second. Then immediately after, for the next 5 seconds, I know that my graph should have a slope of 22 meters per second squared. And so this should give me to this point. Because if I figure out what the final velocity is, actually that is Vx3. If I figure out what that is, that's just the highest point that I reach over here at 15 seconds. And I can prove it to you. So I can write Vx3, the final velocity, equals to Vx2, the initial velocity, plus the acceleration times the time interval. So Vx3 is going to be, I started off at 15 meters per second, and then I'm accelerating at 22 meters per second squared for 5 seconds. So Vx3, my final velocity, much later, is going to be 15 plus 110 meters per second. And that's going to be obviously 125. So I kind of labeled it as a little bit above the 120. Anyways, so that's how that's another way that I know that this works. But let's answer this question by computing the area under the graph. So I need to solve for this area and the area bounded through this shape. So I have this rectangle on the bottom, and then I'm going to have this triangle and this rectangle down. So in total, the displacement is going to equal to area 1 plus area 2 plus area 3. I'm going to label this A1, A2, and then A3 down here. So let's go ahead and do that. Area 1 is going to have a base of 10 seconds multiplied by the height 15 meters per second. Area 2 is going to have an area of 1/2 because it's a right triangle. The base is 5 seconds long because from here to here it's only 5 seconds from 10 to 15. The height is going to be 110 plus the area of this last one. I still have a base of 5 seconds plus a height of 15 meters per second. So the displacement for the entire motion, I'm going to add this all up. You can check this work and you're going to get the same answer, 500 meters. So I could easily model this motion graphically and immediately just get the answer and skip all of this kinematic work and the pictures that we did. And that's another reason why graphs are so useful and they are such a powerful tool when analyzing motion. The last thing for today is a try it yourself. So the try it yourself question reads, a skateboarder starts from rest and accelerates at 2 meters per second squared for 4 seconds. Then the skateboarder continues at a constant velocity for another 6 seconds. How far does the skateboarder travel, and what is the final velocity reached by the skateboarder? So that is going to wrap up today's lesson on solving one-dimensional motion problems. Be sure to attempt the try it yourself question and put your answers in the comment section so that I may check them out and respond to you. Thank you for watching, and don't forget to like, share, and subscribe for more physics tutorials. I'll see you in the next lesson.